energy on a daily basis, and so if those numbers are equal, then you are going to essentially maintain the same body composition. Whereas if you are taking in more than you are expending, then you are going to be gaining adiposity. And if you are taking in less than you are expending, then you are burning through your storage reserves. Now, that's it's a useful heuristic, but it really doesn't describe much of the nuance, because part of the issue, we won't get to go too far into this. As I said, this is more like hormones and behavior rather than kind of like endocrinology type of things. But notice that all calories are not necessarily created equal. But for our purposes, again, we can sort of focus on the idea that if we take in excess energy, we're going to store it as adipose tissue. And the amount of adipose tissue that we store, again, it's not really we're storing adipose tissue, we are filling our adipose tissue with long-chain fatty acids so that they can be used later, right? So we also, and this is kind of a kind of key idea here, that from an organismal perspective, we want some way to know what our energy balance is, right? How much we have in storage kind of at any time. Now, when you've probably seen lots of kind of diagrams like this, there are many in this book, and almost every other textbook has something like this. Well-fed state versus fasted state. And notice essentially just as a kind of big picture reminder, the molecules we take in, the things that we eat, have to be broken down into very small molecules, small enough that they can readily be absorbed into the blood, right? And so all of the sort of magic happens in the blood itself, and so the body, from a homeostatic perspective, is very concerned about the general composition of the blood. And so in our kind of classical well-fed state, we are breaking foods down into the sort of major products, sugars, particularly glucose, free fatty acids, and amino acids. Now, in this particular state, and again, this is a high glucose state. Glucose will be used as the preferential, right? If glucose is available, the body will use glucose, right? And that's kind of really an easy way to sort of think about that. It's not necessarily always true that you just use glucose, and we'll talk a little bit about that going forward. So in this scenario of being well-fed, insulin is being released, and glucose is being converted into both long-chain fatty acids, as well as being stored as glycogen. Okay, so and this is well-fed, and this is a well-fed. The example here is a well-fed carbohydrate-based meal for the most part. Right? So that's actually very critical. As I said, calories are not all created equal, and they don't create the same types of states in the body. The fasted state, again, so in the fasted state, you have the secretion of glucagon from the pancreas. Glucagon is going to cause the release or the conversion of glycogen into glucose, and that is going to be exported from the liver. But you also have lipolysis underway, and so in that scenario, lipolysis is cleaving those long-chain fatty acids into free fatty acids. Those free fatty acids are getting turned into ketone bodies, and those ketone bodies are what are being used to power the system by and large. Now, the other kind of key element to sort of keep in mind here, and again, this is more of like a big picture piece, is that your body always needs to have its base amount of glucose. And so if you are fasting, or if it's the fasted state persists for a long time, you are going to, in addition to liberating glucose from glycogen, you are going to be making glucose in the liver. This is gluconeogenesis. You can make glucose from free fatty acids. You can make glucose from amino acids, right? So the body will maintain a concentration of glucose. If that glucose level drops too low, that's really bad. obviously. It can lead to coma and death. So the body actually really carefully regulates the amount of glucose in circulation. Typically, the way that modern humans eat, we massively increase the amount of glucose in circulation on a regular basis. So we call that a fasted state or a well-fed state, but that's literally just because of the food choices that we make by and large. So if we start getting into the sort of endocrine components of this, notice that when we think about a meal, the endocrine system is actually involved before you actually start eating, right? So this is typically called the cephalic phase or the anticipatory phase. And we are really more or less preparing the body for the meal. And you have lots of hormones that we're going to talk about. GLP-1, ghrelin, insulin. Ghrelin is your hunger hormone. Insulin is oftentimes secreted before you actually eat anything at all, right? So, digestion, in a sense, and this is kind of a weird way to think about it, but really digestion and metabolism begin before you actually consume something, right? And so that's kind of the message here, and one of the, so to say that we're not good at energy balance, like from a human perspective, I think at an epidemiological level, that's kind of almost self-evidently obvious, right? That obesity rates are increasing, and this is actually a demonstration of childhood obesity as a percentage of the population. And so we could look at these, and as biologists, we should look at these and start to ask questions about why these things are happening and sort of what it is about our environment and how we consume food that is essentially causing this. And in other times I've talked a lot about, you'll hear me talk a lot about other classes, right? The food pyramid, right? Everyone's seen this food pyramid thing, right? I saw it when I was a kid. It was released in sort of 1980, and it told all of us to eat carbs and not fat. And so what did we all do? We ate carbs and not fat, and so what happened to us as a population? We got fat. Right? And so it's so much of an issue that they've actually started to keep changing the pyramid, right? They've changed it. They every few years they keep rolling out with like a new one that this time it's going to solve it. But the reality is that as long as carbohydrates are the base of our diet, it will never be solved, right? They can mix and match as much, but and hopefully, as I said, we'll talk about why maybe that's the case. But from the endocrine perspective, I would say that it's probably not that we eat too much. It's just that we eat the wrong things consistently, and we eat them in huge amounts, right? And I say this because if you think about one of the, like, energy balance and actually feeding itself and digestion is one of the most complicated processes, and it involves the contribution of an enormous number of hormonal players. So I do want to introduce some terms that if you're not familiar with them, they're critical that you kind of understand what they mean. And those are orexin, right? So it's kind of up there on the board, I'll write it again. Orexin and anorexin, right? So orexin and anorexin. You need to be familiar with these terms and to be able to describe whether or not a molecule, or at least just classify whether or not a molecule is an orexin or an anorexin. And so the kind of key idea here is that an orexin, right, increases feeding. Right? An orexin increases feeding, and an anorexin decreases feeding. We'll also typically call, right, anorexins satiety signals. And as I said, so from the perspective of this class, our focus is kind of necessarily a bit limited, but notice that you have essentially two signals which are controlled completely independently from each other. They're integrated together, but they're different signals, and that is you have a hunger signal and a satiety signal. You have a eat and not eat signal. You have an orexin, or a set of orexins that tell you to eat, and a set of anorexins that tell you not to eat, to stop eating. And so oftentimes this is a challenge from the kind of subjective perspective to understand, because if you get rid of the orexin signal, what animal does that produce? An anorexic signal, right? So the lack of drive to eat produces a very anorexic type of phenotype. Now, the reverse is also true. The lack of an anorexic signal, right, a lack of a satiety signal produces an obese phenotype, right? And this is, for lots of physiological processes, these things are separated within the context of the hypothalamus. But notice it's the satiety signal that is key for the stopping of feeding, and the orexic signal, the signal to eat, is necessary to consume calories at all, right? So no orexins lead to an anorexic type of phenotype, and no anorexins lead to a very high adiposity phenotype. Okay, so we'll focus a little bit on insulin, but notice there's like a ton of these, right? And if we think about, we're not gonna go through them, and I'm not trying to tell you that you should memorize this list. I'm just kind of trying to give you a sense of the way that we should think about energy balance from a hormonal perspective, right? Which is our feelings of hunger and satiety are derived from hormonal signals in the brain, right? Everything that we feel relative to food is endocrine, right? And that in and of itself is kind of, if we start to think about this, whether we think about it from the clinical perspective or just from the behavioral perspective, notice that all of the signals that tell us to eat, to not eat, how much we should eat, all of these things are being integrated in your brain, but they exist peripherally. So notice when we're talking about insulin, I'm not going to go through in great detail the mechanics of insulin. Right? We'll talk a little bit about insulin. I mentioned already this cephalic phase. So if you smell food, right? If you see food, advertisers know this, right? This is why they try to make the food way better than it ever looks when you get it on TV. This triggers an endocrine response. And so the idea here is that when we trigger an insulin response, the body is essentially preparing to metabolize the food coming in. Now, from the logic of the system, why is it doing this?
Because it needs it, in a sense you need the energy, right, from the food that you eat.
Well, so that's an interesting way to think of it. So you need the energy. Do you need this energy? Is that what the system is doing? I think it's a good idea that we should really think through. So, when is insulin secreted? When glucose is too high. So what do you have to do if what does the system have to do if glucose gets too high? Yeah, you have to take it out, right? Another way to think about this is you have to take it out of the system. Now, why do you have to do that? So we're like on the cusp here. Partially. Why do we have to get rid of excess sugar? Balance. That's a nice way that you put it. Balance. Everybody likes balance. I'm not trying to give you a hard time, but balance. I want to argue that it's because high amounts of sugar is toxic. right? High amounts of sugar is toxic, right? It's, right, think about anything related to metabolic disease, right? It's high sugar that is, hyperglycemia is terrible, right? But, and so think of this, right? So what does the system want to do? It wants to maintain the set point. Can it do that without you ever eating any carbohydrate at all?
Yes.
We've got lots of no's, lots of yeses. So, if you have to eat a sugar, what would we call that? So, are there amino acids that we can't make? Yes. What do we call those?
Essential.
Vitamins. Actually, so we got vitamins. That's a different thing that we also can't make. To be fair, we call them essential. Right. So there are, now keep in mind, so there are essential amino acids. Right. You've heard that term before. It has a very specific meaning. It means that we can't make them ourselves. Right. The whole idea with vitamins is that these are molecules that we need in small amounts. Why?
To make amino acids.
For different reasons, but the thing is, we need them, but we can't make them. Right? Yeah, everyone's got that? Right? So we need also take in things like iodine and iron and all these things that we need from the diet because we can't make them. Are there essential fats?
Sure.
Yeah. So does anybody know some of the names of these fats? Omega-3, that's a great one. Can't make omega-6 either for what it's worth. So, but they never talk about that one because we eat so much of it, it's never a concern. Right? Are there any essential sugars? Got some yeses, such as?
Monos?
Monos?
I don't know.
Like, did you just make up that sugar? Okay, so the answer to this is that there is no essential sugar.
Okay.
Just in case anybody starts to look at monos, people are going. I know I got a head injury the other day, but I could have sworn I never heard that. Okay, so, do you need to take in sugar? No. What will your body do if you don't take in sugar? Break down. Another way to say that is make sugar. Now, do you need to break down muscle to make sugar?
No.
No, you don't. Where can you get sugar from?
Fat and proteins?
Fat and protein. Right? So when we think about, right, so now one of the challenges to think about, now again, I'm not, I think we should think through what the system is doing. So why is the system releasing insulin ahead of time? Yes? Yeah, you want to go ahead? You got it? You're like looking over there at the
No.
Go for it. Go for it. Go for it.
So it can get rid of the extra sugar?
Yes, because it knows you're about to poison it.
Okay. I thought
And,
you were wrong.
and so, but like I said, so yes, we know the system is doing this. Why? Right? The system really does not like. So if you think about, the system does not like excess sugar in circulation. It does not like to be above the set point. But notice if you leave this to the pancreas itself, there's a lag time, right? And meanwhile, if you, as we often do, and I'm not saying that I don't do this too, if you eat a high glycemic index food, what's your blood sugar going to do? Spike quickly, right? And so once we start to see that that's bad, right? We know that it's not good from the sense that that's what happens to diabetics. They lose the ability to metabolize and to store and to do all of these things with sugar, right? And notice that all of the effects, right, all of the negative physiological effects of diabetes are the result of what ultimately?
High blood sugar.
High blood sugar. the sugar is actually being the thing that's doing the poisoning, right? It's not the lack of insulin, it's the hyperglycemia that is causing all of these downstream issues, inflammation, cardiovascular disease, poor circulation, right? Yes?
With diabetes and stress, is it because the chronic stress is limiting the release of insulin? Because you did mention the chronic stress.
Increases cardiovascular disease. So the problem with, so interestingly, this is the issue. It's a great question actually, and it doesn't have a really easy answer. But one of the things that's important to remember, so what kind of, and so this is nice, what kind of hormone is cortisol? What is cortisol doing? Okay. Yeah, it's a, okay, yes it is, a stress hormone. And so anytime you face a stressor, what do you throw at the problem? Energy. So when we think about cortisol, like I said, I think almost, if you ask everyone, their first answer is it's the stress hormone. But so how does the stress hormone help the organism deal with the stressor is the sort of follow-up question to that. And the first answer to that is cortisol is hyperglycemic, right? So cortisol releases glucose, right? And it antagonizes insulin. And so notice that if we take the kind of evolutionary logic of the system, when cortisol is high, right, especially for long periods of time, that's how systems deal with droughts, right? That's how systems deal with famines. It's dealing with cold winters. You need this energy to, whether it's to keep yourself warm, whether it's to more efficiently liberate, to, like I said, making energy available. Now, the problem comes for how do we often deal with stress? We eat. And are we usually eating the best possible thing when we're stressed? No. But so what you have is you're pulling both sides of the lever at the same time, right? And so stress contributes to metabolic dysfunction, not in an obvious mechanism to mechanism kind of way, but it's kind of two diseases of civilization: chronic psychological stress and chronic high carbohydrate consumption. And from a mechanistic level, those two things are opposed, right? So you can imagine that the trying to pull like on the gas and the brake at some point makes the metabolism go sideways, right? Something's going to break, and this is why high stress contributes to metabolic disease in a huge way, because it's antagonizing the insulin. And so what is the pancreas going to try to do to respond? Release more insulin. And so you can kind of see this, and you're not wanting uptake in the liver, right? The cortisol is trying to get rid of glycogen and send more sugar out there, because notice that cortisol is not paying attention to the amount of circulating glucose, right? Cortisol is paying attention to the ACTH, and ACTH is, responding to CRH, and CRH is responding to whatever you perceive in your environment. Right? And so you have this decoupling of systems at cross purposes, which lead to metabolic disease, and oftentimes one of the sort of key hallmarks of this is the deposition of fat around the organs. Whereas normally if you're eating and you're metabolically healthy and you eat too much, right, you put it into subcutaneous fat, right? That's the insulin responsive, that's your reserve. Whereas if you have this sort of long-term, essentially, antagonism from cortisol, you start depositing this fat around your organs, right? Which is, again, downstream of a lot of terrible things. It becomes very inflammatory. Yes?
So, side question, so like when you have diabetes, the high blood sugar, so I want to say I've heard like they say like you're going to get like cuts or something, like amputations or stuff like that.
Yeah, so diabetics, so part of the problem that diabetics face is high amounts of cardiovascular disease and also very poor circulation. So one of the challenges with diabetics is that So notice diabetics are slowly being poisoned by the sugar levels, right? They're being poisoned by the sugar over time. And so when we say poisoned, like everybody knows, okay, that's bad. But when we look mechanistically, what's actually happening is that in the lining of your blood vessels are accumulating sugars. They are beginning to produce inflammatory agents, and so your circulation gets compromised because essentially your blood vessels and joints and all of these things become inflamed. And so in the past, so my grandfather was a type 1 diabetic, right? The bottom of his feet were black, right? And so it's a situation where you have poor circulation, which is the result of inflammation, and and so this is why metabolic disease is usually, in many cases, upstream of cardiovascular disease, because it's not a very far, like hop, skip, and a jump. Do you have these inflamed internal blood vessels, and what do? They collect things like plaques made out of calcium and all of these things, right? So it's like you get this metabolic disease leads to inflammation leads to cardiovascular disease, and so yes, so circulation is a real problem, right? But again, I think one of the things that we have to remember is that, again, we don't think of sugar as poison, and we think of, like I said, these are nice, like we're gonna balance it out and all of these things, but it's actually high blood sugar is not good for the body, right? Generally speaking, and this is why one of the things that they recommend for type 2 diabetics, and kind of as a general rule, is they have this way to describe food that has carbohydrates in it, and it's the glycemic index, which is essentially a measure of how fast whatever it was that you ate can be digested and absorbed. So if you have like classic, like if you have like a candy bar or something, that is a very high glycemic index because it's not hard to digest, right? It's essentially already sugar that's unbound, right? So it hits the small intestine and it just, boom, right? It just goes right into the blood and it spikes your blood sugar. Whereas if you had something like a complex carbohydrate, maybe something like brown rice or something, right? Same amount of, you can make the same amount of, it's the same amount of calories, but because the rice is difficult to digest, meaning it takes more enzymatic steps and, right, the bonds between sugars. So carbohydrates are just sugars bound together. Like how tightly and how many and how complex the structure just determines how long it takes those to be broken down into simple sugars. So the long ramp allows the system to basically remove the glucose as fast as it's coming in, right? Now, if you spike your blood sugar, right, it's difficult for the system to respond fast enough to pull it all out before it becomes toxic, right? And again, one of the, not to harp on this issue too much, but one of the things that makes obesity so difficult to treat is that, as first off, because it's not simply calories in, calories out, as like I'm trying to sort of describe, like what calories are going in has a huge influence on all of these sort of downstream metabolic processes. But the issue is that obesity, especially when you get the sort of organ fat, is very inflammatory. And so obesity is an inflammatory condition, right? And so inflammation, again, is upstream of almost all of the bad metabolic disease and sort of all of these pieces that are downstream. And the system, and what I'm trying to get across, is that the system is trying to prevent this from happening. But man, sugar is awful tasty, Those high glycemic foods are awful tasty, right? And so they take advantage of things like the dopaminergic system and all of that to make sure that we eat as much of those as we can. Now, notice, again, this is also kind of an important idea, right, as a biologist, I think, to have, which is what kinds of foods do we crave? Like, what do they have to have in them for us to really want them?
Sugar, salt.
Sugar, salt and fat. And so salt, as we know, hopefully, now we know, is kind of depends on how much aldosterone we have circulating a little bit. But notice that nobody said protein. Now, that's important, okay? Not because, can you store protein? Like if you eat too much protein, will you store it anywhere? No. If you eat too much sugar, will you store it somewhere? Yeah. If you eat too much fat, will you store it somewhere? Yes. Right? So what is your system prioritizing? It's telling you that things that you can store are good for you, and you should eat more of them. Right? And so it's an interesting sort of, there's a strong evolutionary logic for you should overeat things from our subjective experience that taste good. But from the system's logic, you should overeat foods that you can store for later. Right? Because we don't eat, or sort of our ancestors most certainly did not eat 3 square meals a day at 9 and 12 and 6. Like that never probably happened. Okay? All right. We kind of belabored this already. Insulin and glucagon, you've got these 2 cells in the pancreas that, regardless of whether we're talking about the cephalic phase or not, that these hormones are active or being secreted. The cells are secreting the hormones in response to the actual amount of circulating glucose, right? So if glucose drops too low, you're going to get glucagon secretion from these alpha cells, and if glucose gets too high, you are going to get much more secretion by beta cells. In our modern world, beta cells get much more work, whereas probably in our ancestral condition, the alpha cells were much more active. So you've got this sort of postprandial phase. This is immediately after you eat, and then you have the post-absorptive phase. And again, post-absorptive means that it's after it's already gotten into the blood. Right, so absorption is the getting it into the blood, right? And the postprandial phase is, obviously like the digestion part. Right? The postprandial phase is the important part because obviously, or I should say, it's important to keep in mind that nothing you eat that is in your digestive system is technically in you until it gets absorbed, right? The digestive tract is technically, from an organismal and sort of a biological perspective, the outside world. It's just our connection to the outside world. So, insulin, I'm not going to belabor this too much because I think we have, I should hope that you have a kind of relatively good idea of what insulin and glucagon do from, I would assume from other classes. This is not the first time you've met these 2 hormones. Insulin allows the body to store glucose. Right? And this is important. This is important for muscles often because muscles are not often well adapted to fat, and so it takes time for your muscles to use fat instead of glucose, whereas if you have excess glucose, so basically you've heard of the idea probably of like what's called carbo loading, like if you're a runner or if you have a competition. So the idea is that the night before, what you need to do is do a small workout, spike your insulin right afterwards, and then you will absorb, your muscles are sort of pre-primed to absorb a ton of carbohydrate and then to store it as glycogen, which you would conceivably use like the next day, right? It's not something you do like multiple days in advance, but this is the kind of idea. It allows the muscle particularly to take in and store glucose as glycogen. And glucagon, it converts glycogen to glucose and it induces lipolysis as well. Okay, so we're gonna get a little bit into the neurochemistry after this. I just wanna, this is kind of a fun thing that goes to a little bit about the way that the body uses different fuel sets. And so there's a phenomenon called insulin-induced feeding, okay? And this is that essentially if you have like a rat, or this would technically be true of a human as well. So I mean, you just inject insulin. Like if you hadn't eaten a meal and I just inject insulin into you, notice that it's going to crash your blood sugar. It's going to crash your fuel, and it's going to induce you to eat. Right? This is the basics of insulin-induced feeding. And so this is to ask the question, well, what part of the body is responsible for the inducement of feeding? And then another way to ask that question is, what part of the body runs out of fuel that drives this insulin-induced feeding? So we're going to have two different fuels that we're going to give with insulin, neither of which are glucose. We're going to give ketones with insulin, and we're going to give fructose with insulin. Now there's a really important thing about fructose that you've probably heard before, but if you haven't, it's worth noting, just in general, is that we cannot digest fructose directly. Many animals, including almost all of the other primates, can. We have a pseudogene for an enzyme that would allow us to do this, but that enzyme in humans is non-functional. So what it means is that all fructose has to be digested, right, through fermentation in the liver and converted into fat before it can be used as energy. So the liver can use fructose, but no other tissue, and the tissue in question here is the brain, right? No other tissue can use, right, fructose except for the liver, but the brain can use ketone bodies. It doesn't need glucose, right? It can use ketones just as well, and essentially ketones are used for cellular respiration. You get like 32 ATPs for every ketone body, whereas for glucose it's like 36. So it's a little bit less efficient, but not dramatically so. Okay, so idea, we're gonna find out what organ is responsible for insulin-induced feeding by injecting glucose and ketone bodies and asking what the animal does, and then glucose and fructose and asking, does the animal eat? Do we block insulin-induced feeding? And the short answer is that fructose inhibits glucose-induced feeding, meaning that, and ketone bodies don't, and so the idea is that it's actually the liver which is generating the feeding response in the sort of insulin-induced feeding capacity. Okay. Now, we haven't really talked about leptin yet. We are going to be talking about it in the context of some of these other signals as we kind of go forward here. So these are generally speaking satiety signals. So we have two sort of pathways. We have the adiposity signals. This is typically leptin, right? And so leptin is secreted in proportion to how full of fat your adipose tissue is. So what we mean by that, so when you store fat, the first thing is to not make more adipocytes. It's to fill up the ones that you have, right? So adipocytes are like, the metaphor that always helps me to understand this, and again, you can come up with your own, maybe a better one. If you have a better one, let me know. But adipocytes, right, the cells themselves are like balloons with like a nucleus on them. And so what you're filling that balloon up with is long-chain fatty acids. So the balloon gets bigger and bigger, the more energy is stored. And so how fast does your fat content, right, your overall energy storage of fat, how quickly does that change?
Not bad.
It's not fast, right? Everyone's like, I don't know. I'm sure it's not as slow as we would like, or not as fast as we would like, but so the point to ask that question is, notice that adiposity, or sort of how full your adipose cells are of free fatty acids, is a reliable and relatively stable metric over the course of days at least, right? Days to weeks. So you can have a pretty static signal of how much reserve you actually have. And so that's essentially how leptin works. Then you have these signals coming in from the periphery. Right? These are signals coming through like the vagus nerve, for example, and they respond to circulating amounts of energy as well as things like distension. So as your stomach fills with food, notice your stomach is actually going to stretch. That activates stretch receptors, which feed back onto the brain to tell you to not eat as much, right? You have CCK, which is another, it's sort of released by the duodenum of the small intestine. It's involved in the digestion of fat, but it also acts on the brain as a satiety signal. So these signals are sort of feedback from the body and from the adipose tissue to tell the body how much energy you have in long-term storage. And these are all going into the hypothalamus so that they can be integrated to decide whether, now again, remember, what are we deciding here?
Keep eating.
Whether we should keep eating or stop eating. Right? This is what's being integrated. And you're taking information in from the digestive tract, you're taking information in from your sort of long-term storage capacity to decide more or less whether you should stop or continue to be eating. And so this is all integrated into your hypothalamus, and particularly we are going to focus on the arcuate nucleus. Right? So the arcuate nucleus, that's the arc underneath hypothalamus. The arcuate nucleus is involved in essentially, this is kind of a, an interesting way to sort of think about it. The arcuate nucleus is what decides more or less whether you're hungry or full. Right? It's the arbiter of that feeling, and as it projects, and it is going to project to places like the PVN, its activity in the PVN and lateral hypothalamus is what determines whether you're going to stop eating or keep eating. Right? And notice that this information is translated to you as a feeling. Okay, and so, as I said, we've got our PVN and our lateral hypothalamus. We've got our signals coming in, our stimulatory signals and our satiety signals, and these are interacting with, we've got a set of, say, feeding signals. So I think this is on another slide, but we have our NPY and agouti-related protein. This is our feeding signal, right? Our orexic signal. Whereas OMC and CART are satiety. So this is our satiety signal, okay? And when and on this slide we see insulin and leptin coming in. Notice that insulin and leptin are inhibiting the feeding side and stimulating the satiety side. Right? And this is just, again, a reminder that we can see at multiple levels of the system's organization that hunger and satiety are separate signals. Right? It's not that you feel full when your hunger system turns off. You don't feel full until your satiety system turns on. Right? And so insulin does some of this work, right? But we're going to focus on leptin as a useful satiety signal. And the reason is because if we knock out leptin, we end up with this phenotype of our guy here on the left, okay? Now, again, notice that one of the main concepts, if you haven't been exposed to this before, is that hunger and satiety are separate things, right? They don't, right, again, they don't directly interact. And so the leptin knockout mouse was discovered, or leptin was discovered in sort of 1995, and this is a lack of a satiety signal. There is actually a very rare condition in humans where you have a gene variant which does not produce leptin. And we have 3 children here, and this is the A. Those are, I think, 3 years apart, right? But the individuals who don't produce leptin have to take leptin the rest of their lives. Okay? But the addition of leptin will change their body composition and will allow them to eat less. And so this is what's kind of shown here in B. Notice that this is energy intake per body weight, basically, per kilogram. So how much energy you take in per kilogram lean body mass. And notice that just treating with leptin, now all 3, A, B, and D, are leptin deficient children. And so the issue is, again, the phenotype shown here on the left side of A is that they consume more food than necessary. Yes? Okay, sure.
What did you just say? You said the addition of leptin changes body composition and what?
Oh, I don't know. Food consumption, I think.
Okay.
I mean, it seems to fit in there as a fill in the blank. I can't say that's exactly what I said, but that's the idea, right? So our children who are leptin deficient, again, they're not going to stop eating anymore, right? Their whole satiety mechanism, their long-term. So another way to, what does the body think, right? If you have low leptin, what does the body think is going on? There's no fat. But what does a lack of leptin tell you? You're starving to death.
Right.
And if you are faced with a plate of food and you've been starving for 2 weeks, like, what should you do to that plate of food? You should eat it all. Right? And so notice, again, this isn't like a cognitive decision. This is the system saying, okay, this is how much energy balance, this is how much we have in reserve. If your body says you have nothing in reserve, regardless of how much you actually have in reserve, you're going to be hungry and you're going to keep eating. Like, imagine how challenging it would be if you just never felt full. Yes?
For those people that are on like 600-pound life, like how does, if they don't have a leptin deficiency, how does that work? Because they eat like a lot and they be hungry.
They do. So typically, so it's a great question. So
They'll think like, I gotta eat 3 whole chickens. Like they feel like that, you know?
I question whether or not, so there's a couple of issues here. So let's address the big picture and then maybe we can focus on my 600-pound life after that. Yes? Yeah, so that's, so that's actually exactly
They're
how
not
it's going,
deficient,
which
they're, like,
is
sensitive.
that when the leptin knockout was discovered,
Okay.
right? This was a time of great celebration because it was thought when the satiety signal was discovered that we now had the cure for obesity, right? That the issue was that we could take an obese person, we could give them essentially the treatment that, like this, and we could stop them from wanting to eat anymore, right? That was the idea. And the same phenotype is true when they found the leptin knockout, the leptin receptor knockout. But the problem is actually very similar to what we see in type 2 diabetics. So in at least early phase type 2 diabetics, the problem is not a lack of insulin. It's the responsiveness of the tissue because of excess insulin over long periods of time.
Right.
And so the idea is that obese people have like 5 to 10 times the amount of circulating leptin, but the receptors are much less sensitive.
Gotcha.
And some of the mechanisms that we sort of understand for this, the model that we have for understanding this is actually, this is the way that pregnant women gain weight. Right? This is a natural mechanism for women that when they become pregnant, notice, and this is kind of a strange thing, and now obviously I've never been pregnant, so I can't verify that this is true, but the idea here is that you're not hungrier but you've turned down all of the leptin signaling. Leptin is a peptide that has to get into the brain, right? Which means it needs a transporter to get there, and it needs a receptor to respond to it on the other side. So in pregnant women and pregnant female mammals, the leptin transporters are turned down, the leptin receptors are turned down. So it's essentially like inducing, it's telling the body that, hey, we're energy depleted. You need to eat more, right? And so notice that when you stop eating, at least partially, there are other satiety signals. It's not just leptin. But notice that that leptin signal is doing essentially what this is. It's turning down what your body thinks is how much energy you have. Because another way to sort of imagine this is that if you've ever tried to lose or gain weight, the problem is your body wants to maintain its current composition, right? And so if you're trying to lose weight, it's gonna try really hard not to let you lose that weight because it's at homeostasis. And if you want to gain weight, it's actually hard to gain weight. You're actually typically going to have to force feed yourself or eat really highly palatable foods to overcome the desire of your body to maintain exactly what it is. There's a current state bias. So obviously that's not great for a pregnant woman. So how do you affect that? Well, one of the ways, and the way that our systems seem to do it, is to basically convince the body that no, you aren't where you're supposed to be. You need to eat all this extra to get where you're supposed to be, right? So I think that is the kind of, we understand that mechanism really well in pregnancy, right? And that's and you can imagine why, right? But the funny part is, and again, going back to the point about these being two separate systems, the lever that's pulled to gain weight is the satiety lever. Right? To turn down the satiety lever. Because when you sit down for a meal, you're like, oh, I guess I'm still hungry. Maybe I should have seconds, right? Because I'm not full, even though you've been induced to eat. Now, when we talk about the 600-pound people, right? Notice there's a couple of things, right? So there's levels to the issues, right? And so extreme obesity in particular is a highly inflammatory condition. So once you get to an obese phenotype, it's not just like energy in, energy out, right? You have lots of essentially inflammatory signals that are preventing the easy loss of weight, because conceivably if you just stopped eating, right, you would lose that weight, but that isn't necessarily the case, right? The joints become inflamed, all of these pieces come. And the other thing is there's obviously a psychological issue at play there as well. And so, so there's psychological level there's some issue that makes them try actively to override the signal that they should stop eating. But there's also the problem that most of what is being consumed is dopamine-inducing foods, right? So things like sugars. Sugars induce dopamine, and it does, and just like an addictive chemical like cocaine or methamphetamine, eating sugar is addictive, right? It can be shown you can make a rat. It's actually easier to get a rat addicted to sugar than it is to get a rat addicted to cocaine. It's true.
Wasn't it in our book?
Huh?
Wasn't it in our book?
Probably. Yeah, some boy. I mean, so it's interesting. It's actually it's kind of challenging to get a rat addicted to cocaine. You'd think it would be pretty easy. It's actually difficult, but getting a rat addicted to sugar is very easy.
Is it difficult because they somehow know that?
Well,
What makes it
so it's interesting. I don't want to get too far. I mean, we've got a little bit of time here, but this is our last lecture, so I guess it's crazy, right? So most individuals, right, and this is human, and so most individuals, and this is individual rats or individual humans. So if you took all of us, there's like 50 of us here, right, and you gave us all like unlimited access to cocaine, only about 15 to 20% of us would become addicted to that. And it's roughly that with rats as well. And the reason is it's a strange RNA interference like protection mechanism, so that most individuals like ramp down how much dopamine, so dopamine controls how good you feel after something. And so in that pathway, there are these identified RNA interference genes. Right? I'm putting genes in quote because typically we think of a gene producing a protein. So these are RNAis that are released when we consume drugs. Nobody knows exactly why this is the case, but about 80% produce enough RNAis to prevent the addicted state from actually forming. Right? It maintains plasticity. Whereas I would bet that probably 95% of us are addicted to sugar. Right?
Just 95.
I wanted to leave it open. I'll say 99. So 49 out of 50 of us are probably addicted, and really it's probably 50 out of the 50, right? But that's the thing. It's easier because it's not as an extreme of a swing, but in our modern life, we're all addicted to sugar. More so even than like caffeine, I would say. But there is a dopamine-based mechanism. So there's, anyway here, okay. It's good stuff. Right? This is the kind of general system, right? The arcuate is your integrator. Now notice, again, you can always eat more, at least in principle. But notice how much easier it is to eat more if it's a high sugar food, right? The override signal is easier because you're actually using something that's outside of this, right? When you're full and someone puts a piece of, I always pick on boneless, skinless chicken breast and broccoli. It's like the least palatable meal. It's good for you, I'm not saying that. I'm just saying if you're eating a full meal and someone says, hey, would you like another serving of chicken breast and broccoli? Chances are you're gonna say, I'll pass, I just had, but if like someone puts like a chocolate cake or something really highly palatable, same situation, you're like, you know what? Just a little bit, right? Now notice, you overrode your satiety signals. Now, how were you able to do that? Part of it is because you are able to take advantage of the fact that you're getting a dopamine reward for the cake that you're not getting for your chicken breast. So this is your sort of normal functioning energy balance, hunger, satiety signal. You have your two levers. You've got your hunger side, you've got your satiety side. They both are in the arcuate. The NPY and agouti related proteins integrate both hunger and satiety signals. The POMC cart neurons only deal with satiety signals. So leptin stimulates our satiety signals. Now, it inhibits the NPY neurons, right? So it has this dual action, whereas our hunger lever only really has one side. And both of these areas produce or project to the PVN, where they combinatorially regulate our subjective sense of whether we should eat any more or not. Notice, again, if you think about the situation, like if you're starving, you feel that. If you are full, that is again a subjective feeling that is generated by your hypothalamus. Okay. Let's talk about gonadal hormones and body weight. And so, we talked a little bit about hormonal birth control in here, right? We talked a little bit about it. Okay. So, what does hormonal birth control contain in it most of all? Progesterone. What does it not contain very much of? Estrogen. So, that is the backdrop for this piece of understanding, right? This little story with our rodent friend here. If you ovex her, she will gain weight, right? Estrogen reduces food intake and body mass. Progesterone blocks these effects, right? Straight blocks them. Now, I think there's a good evolutionary logic for this, right? Progesterone is for gestation. What do you need for gestation? Energy. Right? So if we ovex our female rat, she eats more and puts on some weight. If we ovex her and give her estradiol, we bring her back to her normal body composition. If I ovex her and give her estrogen and progesterone, she still gains weight. Right? If I ovex her and give her progesterone, or just ovex her all by herself, right? The effects are the same. Progesterone is blocking, that's what all these kind of combinations are showing, that estrogen is actually blocking, or progesterone is blocking the estrogenic effects on body mass and food intake. Now, what's the number one side effect of hormonal birth control? Weight gain. Why? Because, now here's the thing, notice that what you're doing is extending the luteal phase essentially in perpetuity. Right? And that high amount of progesterone is almost assuredly going to cause, right? Because notice we're doing two things simultaneously. We're dropping estrogen and increasing progesterone. So it's almost assured that based on our animal data, that women on hormonal birth control will gain weight. Yes?
Do you think that this could be avoided if, like, if a woman was given, how would I say this? If they started birth control at an earlier age, like, would it have the same effects? Like,
So unknown, right? So typically, right, I would say probably to a certain degree, but it's likely that's because young women are just much more active, right? If you were to compare, right, so there's a couple of ways we could think about this experiment, right? So like a young, healthy, active woman in her teens, right? Maybe she's playing sports, all these things, you may not notice it, but notice that people are regulating their activity based also on to a certain degree on how they feel. It's almost, or at least the best evidence we have, and also the prevalence of weight gain in general. So notice you could theoretically overcome this, right? So imagine that you're going hormonal birth control, and then you also, because you know for a fact that you're going to eat more. So the other way you can approach this is to say, okay, if I know I'm going to eat more, I'm going to have to move more to maintain the exact same body weight, right? And so based on what we know about the endocrinology, that I think is what's happening, right? So maybe the effect size changes, right? So maybe there's a bigger effect. That wouldn't surprise me that the effect is larger on an already slower metabolism. Right? So unfortunately, as we age, right, your metabolism becomes less efficient generally. And so it's easier to put on weight as we age than it is when we're young. Notice also our thyroid hormone levels, our growth hormone levels, everything is really high when you're in the reproductive prime of your life, right? So yeah, but this tells us that without all things being equal, right, you will gain weight, right? Because you will consume more food, and right, that the progesterone blocks, right? So this isn't an effect of things like IUDs or things that don't release progesterone, right? So it's not like all birth control causes increased weight gain. It's that the addition of lots of progesterone and the removal of estrogen leads to, right, reliably, with everything else being equal, right? Again, all things being equal, right? You can calorie restrict, right? But your bias will be, and if you leave an animal alone to their own devices and not like, the rat probably isn't like thinking through these issues, like I need to, am I getting a little bigger? I don't think the rats are doing that. But that's how we can kind of know that what's going on, right? If we just ovex and no hormones, notice that there's no hormones in the ovex, right? The bias is to consume more food, which tells us, first thing, estrogen decreases consumption and changes body composition in that way, right? So if we ovex and give estradiol, right, we're at the same original sort of like leanish body type. But if we ovex to give progesterone, no effect, right? No effect above ovex. But if we give them both, progesterone blocks the effect of estrogen, and that's really the takeaway here. But yeah, I think it can be overcome for sure, right? But notice that you're overcoming a biological bias, right? This is you are simultaneously removing estrogen and adding a bunch of progesterone, and even if it was just progesterone and left the estrogen normally, that you're going to block the effects of estrogen, right, with the progesterone. With androgens, you increase food intake and body mass as well. All right. The last thing that I wanted to, this is really our last slide. It's crazy. Yeah. I know, it just went by so fast. Semester. So what about these ground squirrels is also true of Syrian hamsters. And so these are interesting models for obesity because when we think about obesity, which I think really and truly is the wrong way to think about it, we think about it as calories in and calories out. But that is not how it actually works, right? It's much more dependent and nuanced than that, right? So, and one example of this, and I said this is the one from the book, but it's also true for the Siberian hamster, that they put on fat every year. They go from a lean hamster or a lean ground squirrel to a relatively, I don't want to call them fat, but like, let's say a pudgy version of themselves, right? And so they do this, even if they're kept on the exact same diet. They're not allowed to eat any more, right? Now, how do they do this? Well, what's happening on the sort of back end, on the other side, is their metabolism is changing to gain adiposity in ecologically relevant ways. But they also turn it off in the exact same way. When they go back into their lean season, they are able to utilize those utilize that extra adiposity and go kind of back into their lean scenario. And so this has been, these are models for understanding the sort of metabolic back end, right? So a lot of obesity is, I mean, the interesting part is a lot of obesity-related issues are all on the back end, right? After food has been absorbed, right? And so, yeah, that's all I've got for you. So yeah, question?
Is that because of season changes? Like-
Yeah, seasonal changes, yeah. They like to get insulated, let's say, for the winter. Okay, so we have an exam on Thursday. It's going to cover social behavior, both affiliative and pair bonding and that type of stuff, and aggressive behavior. Then we have stress, and we have homeostasis, which is kind of roughly, right? You've got, endothermy, drinking, right? Osmolarity, and fluid balance, and then really energy balance. Okay? So,
What are the chapters?
social behavior, stress, and homeostasis. I did them out of order,
Oh, okay.
right? And fun fact, that first lecture on stress, which was actually given out of order, I have no memory at all of that.
You have numbers?
I have no memory of it at all.
What about-
Maybe you feel that way as well, but
Are you releasing these slides later? Is this on there?
Are they not out there yet? Okay, then yes, I will. I'll do it maybe here before I leave. Yes. Okay. Which one would you like?
It is over oxytocin receptors and
Probably in a bowl of some kind.
yes, and
I can't say for sure, but I'm guessing it's in a bowl.
Is it?
Here, this one?
so it'll be the next slide. These kind of go together.
Yeah,
Oh, I
okay.
did that. I'm tripping.
So
It's on there.
I am trying to understand, obviously these variables, highly monogamous. So
Yeah. Mhm.
They're bonded, right?
Yeah.
So what I don't understand is how come in figure A, pair there's nucleus accumbens. For a stranger, they're having a high amount of covenant. And for their mate,
Okay, so do you mean from like a kind of a philosophical sense, like what I think's going on, or?
no, just, I would expect the nucleus accumbens for their own partner.
Right.
For them to huddle more.
Right, and so notice that they do, except in the presence of the antagonist. So if we just focus on the nucleus accumbens compared to the combined CSF, right? So combined CSF means we just did all the CSFs and we kind of put them together. But it's a model for if we just looked at the combined CSF and nucleus accumbens and we just kind of took out all the rest of it. And notice that when oxytocin receptors are able to be activated, the animals are getting reinforced by being with their partner. So, okay? So notice that monogamy is supported by a bunch of neurochemistry. So when you have a significant other, right? People like hug each other, right? And they do that in part because it feels good, right? And so in the control situation, it feels good to cuddle with your partner. But when you give the antagonist, you now prefer the stranger. So the drug antagonist blocks the partner preference.
They were given the antagonist.
Yes, so to read the figure, you see this dashed line here?
Yes.
And so on the other side it says OTA, that's oxytocin antagonist. Okay? So again, notice what they've done. So each group of animals, so there's 3 groups of animals, one that has a cannula in the nucleus accumbens, one in the prefrontal cortex, and one in the caudate putamen. And so each animal got CSF, which does nothing, and the drug. So we added up, we just summarized all the CSF and put that in one category, and then everything to the right of the dashed line is getting the drug.
Oh, that makes sense.
So they give the males vasopressin antagonist?
Yes, and they give the females an oxytocin antagonist.
So under normal conditions, the combined CSF is what is.
Yes, that's the combined CSF is control.
Okay.
So 3 years now?
Is there a question about this slide? Okay, quick, I'll remember. Yeah.
So I have a takeaway for this is that oxytocin receptors and nucleus accumbens increases likeliness that like the female will pair bond with their partner.
Well, so technically they're already pair bonded in this, but so I think if we were to kind of change the phrasing slightly, I would say that the oxytocin receptors in the nucleus accumbens, and to a lesser degree the prefrontal cortex, are critical for maintaining pair bonding. Back to your slide. Okay.
I mean, if it's right here, I mean, you keep skipping me, but if it's right here. Okay.
I keep skipping you?
Yeah.
Well, you know, you're forgetting things too, right? All right, so what we got?
Okay, so I'm just trying to confirm the question that this image is asking. Is it asking that does the pattern of oxytocin binding differ between polygamous and monogamous paired balls?
Yes. Mm-hmm. Right? Yes. Spot on.
What was the question?
So he asked, what is the question they're asking? What does the distribution of oxytocin receptors differ between prairie and montane voles? Or monogamous, even better stated, which was, does it differ between monogamous and promiscuous prairie voles? And so the answer to that question is yes, right? They both have the receptor, it's the same receptor, it's just in different places. Okay? So I've left you too long. Now, what can I help you with?
Figure 9-7. It was really more so, in it, but yeah. This thing.
No. Okay. So this is, simply put, it's the difference between osmotic thirst and hypovolemic thirst, right? So in osmotic thirst, right? So it's like a double compartment model. I think we can find it over here. So just there. So just so that we're looking at the same thing. Like this thing, right? So I don't love these examples, but no, like osmotic thirst is that the blood is too salty, right? You've taken something in, like whether it's like the salty peanuts or salty pretzels, or like you drank Gatorade, right? It's too salty, right? That's why typically, unless you have hypovolemic thirst, drinking Gatorade will not quench that thirst, right? Because notice your thirst is generated by, in this case, typically your blood is too salty and it's pulling, right? Pulling water from the intracellular and interstitial fluid type of thing.
Oh, so Gatorade would make it worse?
Yes,
Okay.
right? So if you eat salty pretzels and then drink Gatorade, you will not have your thirst relieved. Yes?
Can we go over this figure again?
Everybody's favorite, yeah. that one took a long time. I was like, okay.
Wait, so just to be
Oh.
clear, the what is it?
Hypovolemic.
Hypovolemic.
Hypo meaning under, volume, right?
Of water, not
Yes.
of water.
Yes, right? Hypovolemic is there's less fluid, right? So think hemorrhage or something like, like excessive exercise in the hot sun. You're losing salt and water, so your blood volume is going down. Hypovolemic is low blood volume,
Gotcha.
right? Osmotic is high blood salt, right?
Because it's pulling water
Into your blood, right?
Okay.
Yeah. And so to fix that, your brain is going to start producing lots of AVP, so that you can absorb more water in the kidney to hopefully dilute your blood.
Thank you.
Sure. Now, there it is. There it is. Okay. Okay. So, what are we interested in here?
I'm not looking for notes. We wanted to know, like, if the rats could, I forgot, But like basically they can do the same thing that the lizard sperm do, behaviorally.
Behaviorally compensate, right. So we wanted to know if we are able to behaviorally compensate for the lack really of, in this case, it's about aldosterone, right? But yes, so just again, I just want to just keep emphasizing that, you know, where it's like water absorption is AVP, salt absorption is aldosterone. So it's like how thirsty you are is controlled by AVP, how salty, right? How much your preference for salt is controlled by circulating aldosterone, basically. Okay, so we're interested in understanding, right, whether or not we can get behavioral compensation and how does that behavioral compensation work, right? Because so the blue line is control, and the control rat likes the preference of about 0.75% salt solution. Right, so 0.75% salt solution, they begin preferring. Now, I know we had a long conversation about what preference is, but so the strength of the preference is really the distance from the line, right? Because again, if you've got two bottles and you drink it equally, that's no preference for bottle A or bottle B, right? If you drink 55% of the time from bottle A and 45% from bottle B, that's a preference for bottle A. So notice that the preference threshold for a normal rat is about 0.75, right? So you have some saltiness that you would prefer to drink than regular water. And you get it up to, it looks to me to probably be about 75%, about halfway between 50 and 100, right? That's your peak. And that's about, what, 1.75 to 2, maybe 2, right? 2% salt solution. So notice the further along the x-axis we're going, we are increasing the concentration of salt. Okay? Okay? And then our adrenalectomized rats, our rats that don't have aldosterone, prefer it as soon as they can taste it, and they never find it aversive. Right? They will, I mean, have you tried to drink, right, you could, you know, make this at your house, try to drink what 4% salt solution tastes like? You're probably not gonna drink much of it. But notice that our adrenalectomized rats are sucking that down like they can't get enough. Like at 2%, notice they're basically at 100%. They don't even touch the other water. And so, is that behavioral compensation? Yes. So has it shifted their preference for salt? Yeah, I would say it has.
So when we're talking about the critical comparisons, would we talk about like where it's at, like you said, at preference threshold, so like the intact ones are like at 0.7.
Yeah.
They like have a 50% like preference, and then if we looked at the adrenalectomized, they have about, I don't know, like a 80-ish, maybe, I don't know, 70.
Well, I would say, I mean, so I would just, so the way that I would, so the critical, so yes, what you're definitely on the right track about comparing elements of intact to adrenalectomized. So for intact animals, the preference threshold, as you say, is about 0.75 or 0.7. Yeah, we're ballparking it here. Whereas the preference threshold for the adrenalectomized rats are at the detection threshold. And over the entire range of salt concentration, they massively prefer salt, whereas it never becomes aversive, right? That's one way to say it, right? Whereas it becomes aversive at about 0.28, right, for intact animals. It becomes very aversive. Right, so notice below the line is aversive, like you're not drinking much of it at all.
Okay.
Okay?
Yeah.
Below the line is aversive.
Yes.
Or more below the horizontal.
Right, the 50-50 line, right? Which means, so if we, think, I mean, if you just, again, so this is why I always find it useful to try to picture what's going on. So aversive means that so if we take like a 3% salt solution, it means that they're drinking like 60% water. So the total amount of water or the total amount of fluid always adds up to 100, right? 50-50, right? Means that they're drinking out of each little thing, like each cup, like equally, right? The further below, it means they're drinking more water than they are salt, right? And so our adrenalectomized animals always drinking more salt by a lot too.
So if I was to say ADX rats are behaviorally compensating because they lack aldosterone, like preferring more salt and sense.
That's good. I think it's a good summation. Yes?
I'm having trouble figuring out the critical comparisons on the figure we had before with the social bonding and variables.
Okay.
Because there's just so, like, I just don't know what to pull for critical comparison.
You're talking about the ones we had with the oxytocin receptors?
Yeah, there was it's 2 graphs. with
Yep.
the combined CSF.
Yep. Okay. Okay. So, what is our question? And so, again, and the reason that I think critical comparisons are important is because if we can frame the question, we can usually sort of figure out like what we should be comparing. So, what is our essential question here? What are we trying to understand?
How, pair bonding is mediated?
No, we know it's mediated by oxytocin. Now, how do we know that? Because in a previous experiment, if I give a prairie vole an oxytocin antagonist to their whole brain, it blocks partner preference. Okay? So what am I trying to understand then?
I don't know.
Okay, does it have to do with oxytocin receptors? Yes.
Okay.
Right? So it's the question is where, because now again, not to just like if you look at the prairie vole brain, right? If I just said if I give a prairie vole an oxytocin antagonist and I knock out their partner preference, and I say, oh, okay, well, what brain region is important for that then, right? So it could be all of them, but it probably isn't. We have some knowledge of the way brains work. It's probably not everywhere contributing to everything. So where are the receptors we should be interested in? Well, let's look on the A top left panel. Well, we've got a lot in the nucleus accumbens, we've got a lot in the prefrontal cortex, and we've got a lot in the caudate putamen, right? There are receptors in high density in all 3 of those places. So we want to know which ones are important. And how do we know which ones are important?
Like longer contact time?
So we know, right? So in a sense, what we want is a pattern that doesn't look like the control. Right? So we know that we found an important brain region because we give the drug and change the behavior. Right? That's how we know that that's an important area. Because so for example, when we gave the drug to the caudate putamen, did we change the pattern of behavior? No. So is that region important for pair bonding? No. There are oxytocin receptors there, but they're not important for this brain region, for this behavior, and we know that because we can give the antagonist and not change the behavior appreciably. Does that make sense?
Yes.
So which areas are important?
Nucleus accumbens and the prefrontal cortex.
Yes.
Okay.
Right? I mean, understand that. So the
Yeah.
comparison is the pattern, right? And you could get all the way into the weeds on this, but basically the pattern for convenience is reversed, right?
Yeah.
Preference for strangers in both cases, and a blocked preference for your partner. Okay? Okay. Aldosterone. Okay, we definitely can. Let's see, so let's handily right here. Okay? All right, so this is actually, in a sort of a strange way, this is actually very similar to the insulin-induced feeding, right? So we have to give a drug to induce an effect. And now what we're interested in is really what receptor mediates the induced effect. Yeah? No? Okay, so notice that to get this, right, to get this increase in salt intake, we have to give a drug. That's the DACA, right? Deoxycorticosterone acetate, I think, if I'm not mistaken. Right? So if we don't give our rat the drug, she drinks what, right? Like 1 milliliter of salt water, right? So notice this is 0.5 molar saline, right? That's not expressed in a percentage, but we have to imagine it's pretty salty. They can it's above the detection threshold, so they don't drink that much. But if we give them this deoxycorticosterone acetate, they drink like 6 times ish the amount of salt, right? So the drug makes them drink salt, right? So then we're gonna see if we can identify what receptor mediates that effect. Okay, so to do that, in simple terms, we're gonna temporarily knock out the receptor that's what the antisense oligonucleotide is for. It's like a conditional knockout. It binds to the mRNA so that and it gets the protein chopped up because that's a viral defense mechanism. And so the scrambled version is a control, right? It just is it's an oligosense, right? It's the same length, it's the same nucleotides, but they're just all like messed around.